Richard, thanks. But Richard Bowden, our speaker today, is not under the weather. He does not have COVID or anything else affecting him. So for me, this is a treat, because partly because I know Richard quite a while, and partly because he just does a lot of good work. So it's just, you know, for me, it's recuperation. So Richard, I will shut up and over to you.
Okay, thank you very much. So you're under the weather. I have no excuse. So, okay, so today I've got far too many slides. So if you're going to learn anything today, it's probably how not to give a presentation, and you should prepare better. But I'm going to try and get through them. I might have to cut some out. We'll see how it goes. But today I'm going to be talking about perception for autonomous vehicles and robotics. Just in terms of brief overview. So I'm going to just bit of history and who I am, and some legacy work, which I think underpins things, which was a project a while ago called Diplex, and then some of the more recent stuff. So autonomous valet parking, some work that we've been doing on BEV estimation, which stands for bird's eye view estimation in the context of vehicles, and some related stuff looking at feature learning, because of course the world's gone deep learning mad now, so you can't move for neural networks, and how that's led on to monocular depth challenges. And all of these things in my head kind of fit together. So who am I? I'm Richard Bowden. As Richard said, we've known each other for a very long time. We both climbed up through the ranks together, haven't we? So I'm currently Professor of Computer Vision Machine Learning at the University of Surrey, where I lead the Cognitive Vision Lab within the Centre for Vision, Speech and Signal Processing. Now, this is a really old photo. This is pre-COVID, so which is a bit embarrassing, because I think there's literally only one person, two people. Anyway, but I'm that one. I'm the old one in the middle. And as I said, I run this Cognitive Vision Lab, which is within the Centre for Vision, Speech and Signal Processing. CVSSP is massive. It was created back in the 80s by Joseph Kittler. It's a really great place to work. Lots of people are working on computer vision, but there's also audio, medical imaging there. So we're kind of broken roughly into these labs. We've just created a new AI institute, and we all. And so that sits quite nicely with the core of research for CVSSP. But like I say, I run the Cognitive Vision Lab, and that C Lab covers things like robotics, autonomous systems, but also human understanding and sign and gesture recognition. It sounds a bit eclectic, but actually it's just, for me, it's all the same. It's all about people, because either I'm trying to understand people, and that's the sign and the gesture recognition, or I'm trying to learn from people. So you'll see that when it comes to the robotics and autonomous systems, it's about learning about human behavior. I mean, so there's lots of things that I haven't put in these slides, but I mean, we've been doing some work recently, which is all about kind of the non-verbal behavior or communication that goes on between when you're driving. You know, when you come down that slip lane, you know the person that's going to let you in, you know the person that isn't. So actually, you know, reading these non-verbal cues and you know, it is all part of kind of autonomous systems, but I'm not going to talk about those today. Two main funding streams. Rich, you popped up. No. Well, I don't mind you popping up, but I thought you were going to say something. So, two main funding streams: sign language recognition and translation, like I say. But today I'm going to be talking about the robotics, autonomous systems. So there's another picture of us. I should have taken some of these slides out. There's just, you know, this is kind of projects over time, but today I'm going to be focusing really just on a very small section of the work. So I said, like, some legacy stuff that was Diplex, which is ancient now, 2007, 2010, pre-deep learning, back when computer vision was just maths. Well, it's still maths, I guess, but it's now maths and black boxes. So, and then some of the more recent work that kind of leads on from that. So Diplex was an EU project, framework 5 maybe. And it was dynamic interaction, perception, action, learning in cognitive systems. And that's kind of where this kind of the Cognitive Vision Lab came from, because it was quite a big funding stream for us back maybe 10 or 15 years ago in terms of EU funding streams. But Diplex was aimed to build a system that could look at driver safety. And so we one of the main partners was Autoliv, and Autoliv in Sweden own a lot of the patents for things like airbags, and driver safety for them it is a big area. But also back then, the idea that we would have cars on the roads driving themselves was just absolute madness, you know. So the closest you would get was something that would comment on a human driver, or would be a driver safety system. You know, things have changed a bit. It's amazing actually how back then the thought that an autonomous vehicle would be let loose on the road was madness, and all it actually took was a little push button that said, "I accept all responsibility, and I need to take over control," and that's enough of a kind of a legal. Yeah, it's amazing. Anyway, so the whole point of Diplex was to look at this driver safety. So actually, Autoliv, this vehicle here. In fact, you can probably see the mouse there. So this vehicle was Autoliv's test vehicle. It had LiDAR, it had cameras, you know, all the stuff that nowadays we would expect to see on an autonomous test bed. You know, but this was space age technology back then. And it also had, what did it have? It had skin resistivity, so it even knew how much the driver was sweating. It had eye tracking, and basically they drove this around Sweden collecting lots and lots of data, which was, you know, very valuable data. So it was driving just in natural scenarios, collecting, you know, the geometry around the vehicle, what could be seen, and importantly, what the driver was attending to. But of course, Autoliv would not let us drive this vehicle entirely autonomously, although we did. I mean, within a small, they had a little mock village where you could drive it, and they could happily sort of like run pedestrians past on pulley systems, so you could drive into them and things like that. But actually, what we did, we wanted something that we could drive in anger. So this thing down here was actually, it was the fastest. It was the fastest remote control car I could get. Did 35 miles an hour before you go to petrol or ethanol engines. It's 4-wheel drive, and basically we just hotwired it. So we had effectively just a tiny little robotic platform that we could drive it up to 35 miles an hour. The first time this was under autonomous control, it did drive itself into a brick wall at 35 miles an hour, which was probably good that we weren't controlling Autoliv's vehicle. But we had these two kind of test beds, and one of the first things we did is we got, you know, because computer science, data is key. We got lots of data off Autoliv for their vehicle, and I was hugely excited by this, because what we had was somebody driving this vehicle around, but also not only what could be seen, but what the driver was attending to. And I got very excited because, we're going to be able to do, you know, lots of things, looking at human attention and working out what's important in the context of driving. And as soon as I got that data, I wrote a visualizer, and the whole point of the visualizer was it just played the video, and it drew a crosshair over where the driver was looking. And it was great. We watched the video, we got very excited. Oh, look, he's looking at, you know, he's looking at the pedestrian, he's looking at the traffic lights, all this. And then I realized there was a 20-second offset between the eye tracking data and the video data. And I took that offset out, and we watched it again, and I was equally convinced that it made sense. And the truth of the matter was that there was absolutely no value in this, or very little value in the gaze of the driver. And that's because if you think about the physics of the human eye, well, most saccades are actually to do with the physics of the eye. You know, if the eye doesn't move, then the eye stops working, right? So quite a lot of eye saccades are just to do with us building this kind of large picture of the world. And so while people do attend to objects, they do it in a minority of cases. And actually, if you think about you driving, what you spend most of your time probably doing is just looking at the horizon, you know, looking at some point of infinity. And most of your driving is going on using peripheral vision. So if we can drive without attending to anything, then surely so can the machine. And that got me looking at things. So there's something called visual gist, and gist has got a different definition depending on the community you look at. So if you go to computer vision, you'll get one definition, you'll get slightly different definition if you go to psychology. But this CV definition is really about, it's low level. Well, it's a load of Gabor filters, right? So, basically, if I take the eye and I just look at filter responses at the lowest level, so, and the idea of this idea of GIST is it's biologically plausible. You're looking at the lowest parts of the human vision system, so V1 through to V4, and it is just a load of Gabor filters, and there's a load of psychophys out there that looks at what the humans can do in terms of visual GIST. So this was some work that came out of MIT, where they were looking at holistic scene descriptors and both the psychophys test that you would do with humans, but also trying to build systems that kind of similar attributes. And if you take these kind of, Fourier transform or Gabor filters over the image, then you can start to do things like classifying whether it's kind of urban or non-urban or inside. There's also some work that was done by Fei Li as part of her PhD, and this also looked at she did some interesting psychophys. I mean, I think the work was probably duplicated within the psychology, within psychology as well, but looking at how long how much information you can get based on how long you look at an image. So the experimental setup was basically point of fixation. An image was flashed, and then the human was asked to comment on what they saw. And in these tests, you had different amounts of times, right? So here's an image here, and you can sort of see that actually whether the human was given about 100 milliseconds or 500 milliseconds, they get a very quite a detailed description of what the scene is. And if you look at this image, there's quite high contrast here. Whereas down in this lower one, you can sort of see when the image is much more cluttered. There's the short exposure time. There's enough time for you to sort of say, well, it's indoors. I know it's indoors, but actually, when it goes up to 5 times as much time, 500 milliseconds, then you start to describe the content of the scene. Now, importantly, this is pre-attentive vision, right? The idea is that the time, 100 milliseconds or 500 milliseconds, is such a quick pulse that you don't have time to saccade or scan the image. It's just sort of like, these images are shown to the eye, so they kind of fill your peripheral vision. So if I can drive a car without attending, just using peripheral vision, and we can glean all of this information again without attending. So, can we build systems that work like this? So back in, when was it, 2007, we did just this. We took these Gabor filters, or we tried Fourier, we tried Gabor filters, and I think they ended up as hogs or something like that. But really, just low level feature responses, rectilinear, over the entire image. We did some clever channel encoding on these, which meant that they were invertible, which means that you could back project back into the image to see what was actually activating the classifiers. And then we did just that. I mean, this is pre-neural network, so we just built classifiers that tried to predict what was going on. So we know that GIST, is good for scene classification. So it's perhaps not surprising down here that it's quite good at doing scene classification. And these are ROC curves. So a random monkey would be sticking a pin in an image would be a 45-degree line, and the closer it gets to this right-hand elbow, the better it is. And so a perfect would be a right angle. So you can sort of see that actually it's very good at choosing the green, which is inner urban, and non-urban, but outer urban less so. Up here, this is so it's particularly good at detecting pedestrian crossings. It's not bad at getting crossroads, not very good at T-junctions, almost a random number generator at deciding when there's a T-junction. But we pushed this as far as we could. So we then started to look at action recognition. So this was about steering. So we could predict not when it would steer, but we could predict very accurately or fairly accurately when it would do a turn left or a turn right. And that's perhaps not surprising when you get to a junction, if it is a T-junction, there's only one way to go. So there's a fairly strong prediction that we're going to turn. We also looked at predicting braking and clutch. Now, I would say braking and clutch are correlated anyway, but it was quite good at predicting when somebody would brake. And when you start to dig into this, it picks up on things like headlights. So when it sees the headlights of the vehicle in front, the vehicle would brake. And this is an example here. So this is an activation map firing for pedestrian crossing, and you can see that the classifier has learned the features here on the road are the thing that correspond to a pedestrian crossing. It has no concept of a pedestrian crossing, but it's learned there's a strong correlation between these features and this class that somebody's told it about. The interesting thing up here is this what looks like a sun, and actually we thought this is just context. So this is just about, for instance, if there's a building there, then it kind of knows whether it's in a city or not. Whereas if you're in open fields, you're very unlikely to see a pedestrian crossing. So actually, looking up at the sky gives you strong contextual cues. We took this forward. We did driver prediction, both in terms of this is a little robot that could learn to drive itself. There's also an example later on with me driving around Surrey country lanes. Oh, it's not going to play. And then we can reverse these the classifiers to see what it's actually attending to, and it actually does what I kind of started off saying. It basically looks at the horizon. It looks at where the road is curving to. Exactly what that driving instructor told me on my first one. Just look at the end of the road, and it's constant, and it's using that as a cue to determine how it should steer. So we took this to its natural conclusion. Actually, we looked. I think this was the most interesting thing, because we could predict human driver's actions with ludicrous accuracy, and we could make predictions about what the driver was going to do much faster than the driver. So before the driver was going to do it. There was also, going back to the eye gaze, we actually correlated the eye gaze. Remember, I said the eye gaze was rubbish, right? But we correlated the eye gaze with the predictions from the system. And I said the eye gaze is rubbish because most of the time the eye saccades are just random. But occasionally, importantly, when I do stop at that traffic light, I do look at the thing. So there are there are times when the eye fixation is incredibly important. And the correlation between what the classifier was looking at in order to make predictions about driving and what the human was looking at were much stronger. You can see up here than this is itchy and knock. So this is at the time a state-of-the-art saliency detector. So a saliency detector, it blew things out of the water. So there was very strong correlation between what the classifier was looking at and what we were looking at. Now, this idea of sort of like taking a bit of human inspiration is kind of common. So more recently, we were working on a project which we called CDAR, and this was about robot localization. So if you've come across MCL before, MCL stands for Monte Carlo localization. It's effectively a particle filter. So there's an example here. Every single one of these red dots is a potential location of where the robot might be. And then for every single one of those dots, particles, observations are measured, right? And it is just a Bayesian filter. So it's just, at the end of the day, it's just Bayes rule sort of being iterated over time and time again. So you take your observations, you multiply them by your prior, and that gives you a posterior distribution. And then you resample from that. So what you can see here is the particle distribution. Although it starts off uniformly sampled, it very quickly hones in on the actual location of the robot. Now, when robots do this, we need some sensor, some way of measuring the world. And quite often that's done with something like a LiDAR. So here we've got a Velodyne LiDAR, and here's a robot position. And what we've done is we've taken this sweeping LiDAR, we've done a 360-degree scan, and then that gives me depth measurements as to all around the current position of the robot. Now, in that Monte Carlo localization framework, I can use that as my observation by measuring how well the LiDAR scan correlates with the map that I have. All right, and that gives me a likelihood that I can then throw into that Bayesian calculation. Now this is, it's not particularly robust to the map, to errors in the map. You need a good map to start with. But it's fundamentally not how humans do it, right? So how do we, doing this would be akin to me walking down the corridor with a map in my hand and a great big tape measure, measuring my distance to all of the things around me, and then looking at the map and try and work out where I am. And that's not how we do it. Now, if I want to go out with an OS map walking, then I don't start measuring distance. What I do is I pick salient features, right? So there's a mountain there, there's a church steeple there, and actually I don't really need to know how far away those things are because I can triangulate my position from them, right? So humans don't do it exhaustively. We do it selectively, and so we took this idea, and that's where CDAR came from. So instead of LiDAR, which is light and detection and ranging, we've got CDAR, which is semantic detection and ranging. So instead of measuring distances, we use, in this case, a neural network to look at the image and come up with high-level classification, right? So I can look at this image here, and I can sort of say, well, this is the floor, this is a door, this is a wall, and then I can use these higher-level semantic cues to match with the map, right? So rather than just exhaustively sort of like trying to do measurements, I can use some of the semantic information. And so, I mean, in practical terms, I could just take a scan line. I can look at this semantic label along this scan line. If I've got depth information, I can turn this into effectively a little LiDAR scan. And then this is me with the map world now, with a simple bit of projective geometry. I can start to try and align these semantic labels, potentially with depth, with the features of the map. To do this, we can do this very efficiently. And we do that with chamfer maps. So actually, what I do, this is a floor plan for CVSSP, and this is my office. That's where I currently am there, and this is the little robot lab that we have right across from my office. And these chamfer maps are effectively distance maps. So these are pre-computed from this map, and it's basically the distance of every single pixel to the closest window, wall, or door in the map. And these are pre-computed just because instead of actually having to calculate things, I can just do a lookup into this chamfer map and read off straight away, if anywhere I am in this image for this point, how close I am to the closest window. It's just a single lookup. And now what I can do is I can use this to basically localize. So I can take my hypothesis of where I think the robot is. I take my image, I run a neural network over it, I get my semantic labels out, I might have depth, and then that just gives me some lookups into these chamfer maps, which gives me a likelihood for that position. And again, it's just a Bayesian filter. So I multiply my prior for that particle by the observation, and then I resample and keep turning the handle on this Bayesian filter. If I don't have any range, and then I can't do a direct lookup, but that's not a problem because I can still scan, fire out a ray into the map world and find the first intersect with that semantic label. If you do this, then this is that particle filter running with these semantic labels, and you can sort of see initially, like that MCL filter I showed you a minute ago, it starts off uniformly sampled, and then very quickly converges. Now, the nice thing about this is that we can get equal accuracy to a LiDAR without using any depth at all, just using the images, because the semantic cues are so strong. The fact that I can see a door or a window or a corner to the building, these are quite strong cues. There's just a little example here. So this is a Turtlebot 2 robot, old school sort of like ROS, with a Connect sensor on it. And you can see here's the image coming in. We're running semantic segmentation. We've got the depth. I'm using I keep using I, but actually this was Oscar's PhD. And then we're overlaying the map, the depth back onto the map to show how well the localization of the robot aligns with well, yeah, how good the localization is. So this worked quite well, and this led on to a project called AVP, autonomous. I just noticed that shouldn't say valet parking. It's valet, as in it's on the next slide. Autonomous valet parking. Woohoo! Spell correction. Right. So this was a project with Eugene and Brian at Parkopedia, and the idea was, if you're an autonomous vehicle, and one of the first use cases for that autonomous vehicle was going to be parking, because actually it's quite a, the use case is I turn up at a car park, or I turn up at my meeting, and then I tell the car to go park itself. It should go into the car park. It should park itself. When I finished on my mobile phone, I would probably sort of say, come and collect me. The car should extricate itself from the car park, come and get me, and I get in and I drive off. And it's quite a good one because the car park can be a sterile environment, so we can take pedestrians out. It's low velocity, so unlike a road where a vehicle is driving at 30 miles an hour, in a car park, it's fairly slow, so it's quite a good early adopter for a kind of autonomous driving. From Parkopedia's point of view, their business is parking, and so building the assets that will support the next generation of parking is important for them. So this whole project was, well, what assets would you need to either create or put into an environment in order to facilitate SAE level 5, for parking. And this is important. It kind of led on from that CEDAR because multi-story car park is probably GPS denied, so you don't have any global localization, and you still can't afford to put a LiDAR on every single vehicle. So if we can do this with cheap, low-cost cameras that's on many cameras now, many vehicles anyway, or can easily be retrofitted, and do this without GPS, then we're onto a winner. So that's what this project was about. And I'll talk a bit more about what we developed. I mean, some of the demonstrators ended up using AR tags. They're cheap and easy to put up, but we spent quite a lot of time building some of the algorithms that would allow us to do this with natural features. About the same time, I had a stinking cold. I was lay on the sofa. It was a Sunday. I was looking up on the internet how to hack a CAN bus. And by the end of the day, I decided that we should build our own autonomous vehicle. Within a week, I'd bought this stupid Twizy car, which is a little Renault. It's an electric vehicle. This is a one-person version. I got the cargo, so I could put a load of computing power in the back. And I basically built our own little autonomous testbed out of this Twizy. It's not dissimilar. You might have come across a street drone, but street drones were quite expensive. I mean, the Twizy cost me about $5,000, I think. I'm not allowed to tell you how much the NVIDIA PX2 cost, but the whole testbed, and it's not fully autonomous, it's largely a data collection platform, cost, I don't know, maybe not much more than 10 grand, I think. 10 or 12 grand, maybe. Yeah, maybe let's say 15 absolute tops, because I guess the LiDAR was quite expensive. But it's a Twizy cargo, NVIDIA PX2 drive in the back. And the NVIDIA PX2 was the onboard machine that all of the earlier Teslas used before Tesla started developing their own platforms. Got 6 of this Seconix cameras. So there's 2 at the front as a stereo pair, and then 4 with wide field of view. So they give 360 imagery all the way around. There's a 64B mouse to LiDAR, some wheel odometry. There's an IMU in there, GPS, etc. And this actually has been quite a useful platform. I mean, it probably nearly led to a divorce because I was in the lab every weekend building it, because I'm slightly mad, putting all of these sensors in. So every weekend I would come in and do it. But it's provided as a good test bed and lots of data capture. So there's This is it. Some pictures of it here. This is while I was building it. This fans to try and keep the boot cool. Yeah, and there's a blog if you want to have a laugh. There's like, as I was building it, sort of like on a weekly or daily basis, there was a little blog that I created, which was me, my little build your own autonomous testbed adventures. This is the sort of thing that it produces. So this is actually a monitor on the back seat. Sorry, on the back door. You've got the this NVIDIA PX2 here. You've got, this is the output from the LiDAR. So you can sort of see within the robot lab. These are the cameras that surround it. So some, I think 4 of these must be the surround ones. These got wide field of view. There must be at least one that's a front-facing camera there. And then this is the output from some neural networks, some feature representations, which I will talk about in a second if I've got time. This is some data that's captured from the campus. So this is LiDAR that's all been registered with SLAM and reconstructed. This is one of the car parks we use within that AVP project. In fact, we've got a paper under review at the moment, which I need to be careful about because I don't want to break anonymity. In fact, oh no, it's not anonymous anyway. But anyway, we've just released a massive data set that we captured with this car, and also a digital double. So not only the data, the visual imagery and all the LiDAR, but also some digital twins with 3D models, and also the whole software that you can generate. Synthetic data that aligns with all of this. So that's currently under review. Hopefully that'll be accepted soon. Now, going back to that project. So what we wanted to do was localize within a car park, well, let me ask it. I'll go straight onto this. So we came up with this idea called convolutional odometry, right? So what we want to do is we want to localize the vehicle just using images alone. So no GPS, no LiDAR, nothing like that. And there's 2 stages to that. So the first stage is about taking an image and then instead, well, basically generating it a position on a map, right? And so what we've got here is some images coming in, and then we've got an encoder decoder network that instead of producing another image, produces a position in space, right? So our image comes in, it's encoded to some latent space, and then we decode, but we decode to a map effectively. So it learns for every single image where that's likely to be in space. We can take different images across the decode because these are at different scales, and this effectively allows us to build a probability distribution, quite a nice distribution of how likely we think we are in the parameter space. And that parameter space could be XY on a map, or it could be XY theta. It depends. And this has been done before. So there's other people that have tried to do this absolute recognition. You know, it's just a neural network. And this is on the Cambridge Landmarks data set. And you can sort of see here that these are the images in. These are the heat maps that are being produced by that network. And then we can use those heat maps. We can basically take an argmax over it, and that allows us to estimate trajectories. Now, the problem with this is that neural networks overfit, right? And so actually getting to this to generalize between different days, or you know, when the environment is different, the lighting is different, is non-trivial. But we'll come back to that. Now, the next stage is this convolutional odometry. So what we did was, the reason that MCL came about was the fact that it's not tractable. You know, in an ideal world, you would have an infinite number of particles, right? So it's a probability distribution, and I want to represent it with a likelihood. Well, you know, it's continuous, and therefore I would have an infinite number of particles, but that doesn't scale. What I could do is I could make it a discrete grid, but again, that doesn't scale very well. And so that MCL, the particle filter, the whole point is the importance sampling. You only put samples that are the most likely parts of the probability distribution. You don't bother exploring parts of the space that are near zero, right? So you're efficient with where you explore the space. But of course, this part of this network is on a neural network, and now what I've got in a neural network or a GPU is a massive potential for doing parallel computation. And so what we did is we effectively went back to old school. Instead of having a particle filter, what happens if we just have a solid, we basically model, we just discretize space, and we model the likelihood at every single position simultaneously. And I can do that because I've got quite a lot of memory on my GPU, and because the GPU allows me to do computations in parallel. So I can basically maintain every single hypothesis at every single iteration, and use the GPU. And the nice thing here is that this idea of running an odometry process can effectively be implicit in the neural network itself. So this is one massive neural network, even though the first part is something that we would consider a neural network, an encoder decoder, but then it turns into something else. Now, the way this computational odometry thing works is what we want to do is update our likelihood maps over time. And if I've got odometry coming in, then what I can do is I can take my odometry measurements, I can collapse them into a kernel, and then I can convolve my likelihood volume with that kernel, right? So basically update the likelihood. And of course, because this is on a GPU, this convolution is happening in parallel and very efficiently, right? So what we've got is the first part of the network produces a likelihood of where it thinks it is. And then the second part of the network is adding that into the likelihood, but then updating the entire likelihood map over the whole thing very efficiently in parallel. And so this is what we're seeing here. So this is the image in, this is the likelihood, this is the likelihood field that's being convolved on the GPU itself, and then this is just a max over that likelihood field. And occasionally it starts to diverge, you get multiple hypotheses, but it's actually just modeling effectively a single hypothesis of where it is. And this works really well with the multi-story car park, because you do get lots of ambiguity because the levels tend to be the same. So you've got multiple hypotheses, but it'll bring in other cues because it's been integrated over time. So sort of say, well, I can't be on the 5th floor, even though it looks like the 5th floor, because I've come from the 2nd floor. So I must be on the 3rd or the 1st. There's a real problem with this, and this is the fact that you want it to recognize the car park, but actually what it recognizes are cars, because that's all it can effectively see. So we did a piece of work that was looking at trying to make neural networks blind to specific types of objects. So and we do that by putting this is a VQ-VAE, so it's a VAE, and we've got an image coming in and an image coming out, and what we want to do is train the network to remove, or not to remove specific aspects, but to be blind to them in the first place. So we put pressure not only on the output of the network, but also on the latent space to remove any trace of the object that we want. So here's some examples. These are examples where we've tried to make a network that's blind to hats. And here we've made a network that's blind to sunglasses or glasses. And there's lots of examples here. So here's a network that's blind to cars, to people, and you can sort of see how it removes them. They don't disappear entirely, but what we're trying to do is we're trying to encourage the network to encode, to just not to encode the things that we know, the distractors, which in the case of the car park is the cars. And so here you can sort of see that same odometry model, but when we change the encoder now, so it's the encoder that was trained within this neural blindness scheme, we get a performance increase because it's slightly more invariant to the changes in the environment that come from cars, and cars being in different places. Now, running out of time, but this is cool. So there, what we were talking about is taking an image in and then turning it into a map. Now, if you take this to the natural conclusion, you get to this BEV estimation, right? And in fact, this is old. It says accepted to appear. In fact, Avi won. This was the best paper, outstanding paper award it got. But the idea is, can we take an image in and not just work out where we are in space, but basically produce this plan view? Now, from a robotics perspective, this is really what we want, because if you think about, if anyone out there is using ROS, whether it's RViz or Gazebo, all of the systems we build are typically sort of like this god, like looking down at the world. There's a robot, it's a robot centric world with the environment around it, and it wants to know where all the objects are. And so this BEV estimation is about training a network that takes an image in and turns it into this plan, the plan view, because it's much easier for the robot to do reasoning in that space. Now, the way we do that is as a translation problem, right? So we took transformer networks, which, transformers are everywhere now, but originally it was they were there for translation, and we ask that transformer to translate from the image to this plan view. But we do it on a line in the same way that a scan line. So when you do monodepth estimation, the horizontal scan lines of the image typically translate to further and further away from you. It's a sweeping generalization, it tends to be true, but it's also true that as I scan this, the vertical scan line, then it's typically a polar sweep in front of me, right? So our network to do this looks something like this, right? We've got an image coming in. We've got fairly classic backbone, so a ResNet. This is then goes through an encoder decoder, right? And then we do some resampling to move from a polar back to a rectilinear, and then we basically go back in a decode back to the segmented image. Now, the important thing here is the transformer, right? I mean, this is just some examples. So these are some images in. These are ground truth. This is like was the state of the art, and this is what we produce. So you can sort of see it's doing a reasonable job at working out what the layout is. But what's interesting is when you start to look at that transformer. So key part of the transformer is attention, all right? So, and when you start to decode that attention, you can start to see what is it that the network is looking at in order to make its guesses, or where its visual cues come from. So here's our BEV map. So this is the vehicle here. And this scan line is at 10 meters, this one's at 20, and this one's at 40. And this is the attention for this scan line at 10. This is the attention at 40, 20, and this is the attention at 40. And it follows that general sort of like rule of thumb that I said, which is that the further up the image, the further away from the vehicle it actually is. So that is true. But notice it's not a straight line. And actually what you start to see is that the machine looks around objects, right? And this makes absolute sense. So here's a good example here. Well, can't actually see on the images very well. They're very dark. No, but this is a good example here. So here's the scan line, but it's not, this scan line basically goes around the cars. And the reason for that is that if I'm trying to predict something on the ground plane, but that ground plane is obscured by an object, then the only cues I've got to make predictions about what's behind that, where it's obscured, is to basically look for any visual cues over it. So for instance, if there's a vehicle and I want to predict the pedestrian stood behind the vehicle, I need to look over the vehicle to see if there's any evidence of a pedestrian popping up over the top. And that's exactly what you see here. So these attention maps have a prior that they increase with depth, but the machine is using the context of the scene to look around the objects for any cues in order to assess. So you can sort of see, you can see the attention maps here. I think that is a pedestrian. These are pedestrians, and it's kind of looking over. Anyway, there's a nice video here. We took this work on and we looked at building on top of the BV maps, looking at the configuration of objects. In this case, this was using GCNs, and that gave us further performance increases. Very quickly, so I haven't got time to talk about this, but Jamie, who during his PhD spent a long time looking at feature representations. So this was something we called SAND, and these are implicit kind of feature representations that are learned by a neural network, but we could steer them to have specific attributes. So this is a feature representation, and in this framework, by choosing where we chose negative samples from, we could say whether that feature representation is global or local. And these are just visualizations of those feature representations. So that here, it's been forced to come up with a feature representation that is unique globally, whereas down here, locally. And so you can sort of see that this looks like a higher frequency noise, but having these attributes is really useful because it means whether you're looking for, if you're trying to do image to image matching, then you probably want a global representation. But there's other scenarios where you want fine grain local features. So you can put these things together sensibly. But we took this work on. We started off looking at the feature representations like that. We then started to look at something called contextual loss that would allow us to do cross-seasonal feature matching. Here we wanted a representation that ignored whether it was autumn or summer. It doesn't matter whether the tree has leaves or no leaves, or whether it's daytime or nighttime. The feature representation is the same. So we use this contextual loss, and so all we needed was examples with very loose GPS localization, and that allowed us to build these feature representations. And so this feature representation here, I mean, this is SAND, the one I was just showing you, and this is us matching features between day and night, and it fails. This is the state of the art in deep feature matching at the time. It fails. But this deja vu, using this contextual loss, allowed us to learn feature representations that were invariant to lighting and things. So you can sort of see here at nighttime, and here at daytime, we still get good feature correspondence between the two images. We actually took this work even further and started to use these features in monodepth estimation. So I'm sure many of you come across monodepth. This is just about training a neural network to, given an image, produce a depth map. And a lot of the approaches, you can train it supervised, or you can train it self-supervised with losses from either stereo vision or for structure from motion. But by putting some of these extra pressures on the feature representations, you can get much better monodepth estimation. And what that's led to then is Rossini. So Rossini, this project is just coming to an end, and this was a collaboration between computer vision and psychology with a lot of psychophys in there. But Jamie's built on a lot of his work he did during his PhD to build a very comprehensive baseline. So so if you want to do any monodepth estimation, then take Jamie's framework, right? So what we've done is we took not every single, but all of the major mono depth estimation approaches that everybody had published. Everyone, you know, it's like when you write a paper, it's always better. Everyone's better than the state of the art. We unified the entire code base. We put them all in a single code base that allows you to switch on or off every single contribution from all these papers. And what we found, I mean, and it upset some of the reviewers, is that the single biggest effect out of all these papers is the change of the backbone. So as the backbone, you know, when somebody's sort of saying we're state of the art, that state of the art performance didn't come out of all the tweaks they were claiming as their novelty. The actual improvement came from the fact they changed their backbone. But this entire code base is free for you to use and build on, right? And what we've done is we built on top of that code base, and we introduced the monocular depth estimation challenge. And we ran the first one at WACV back in January, and we've got the second one running in Vancouver this year. We took the SINS dataset, which came out of Southampton, which is very, very dense and accurate LiDAR scans. And we used that to produce very accurate ground truth across lots of different scenarios. So if you think of most of the monodepth, people just, it's Kitty, the Kitty data set. It's all autonomous driving. And if you take that I mean, what makes it work are the priors. You take that and you show it an indoor image, it fails or it doesn't do very well at all. And so what we've done as part of this challenge is we've taken that SINS data set. We've got categories, lots of different categories. And so you've got the entire code base. We've got the test harness. You can work with this to try and improve depth estimation for the greater good of people. And we've done all the hard work for you, and you get an instant comparison against anybody else. So I would encourage everybody, anybody interested in monodepth estimation, to have a look at the challenge and also Jamie's code base. Now, I've left loads of things out. Somehow I've managed to do 69 slides in 50 minutes. Okay, so I hope I didn't lose you. I can't thank everybody in the lab, but I think I've thanking here everybody who's contributed to some of the stuff that are on the slides that I've covered. So thank you very much.
Thanks, Richard. Yeah, I'm slightly mesmerized by this video here, which I assume is parts of India. Must be.
I think it might be slightly artificial.
Oh, really? Okay. Yeah. No one will walk that close to a car, surely. Yeah, it's horrifying. Well, that was a little romp, wasn't it, across loads.
Yeah, sorry, it was probably too fast. I did have too many slides. But...
well, I found it very useful and very interesting. It's getting rave reviews in the comments. Now, is Shumin with us? I think he's...
Hello, Richard.
Hi,
hello.
Shumin. How are you?
Yeah, I'm good. Did you get better?
No, but don't let that worry you.
Okay.
You're healthy, that's all that matters. Now, I can see a question from Mark Hanheider. Now, I wonder if can he come online? So, oh yes, he can. Somebody's promoted him, so that's good. Hi, Mark.
Hello, can you hear me actually?
Yeah, we can, yeah.
Oh, wow, you can't see me. Hi, no, Richard, that was awesome. Thank you very much. The first question I had was about the energy efficiency of using something like convolutional odometry. I mean, one of the neat things of MCL in general is it's pretty computationally cheap. And we can run this on even the smallest platforms without affecting the battery runtime too much. If I put a GPU on each of these robots now and do all the probabilities updates in parallel, as one can do, is that really something that's good for robotics? What's your view on that?
Well, I think right. So you're right. It's perhaps not cheap, and you do need a GPU. But I think the whole point there is it was a single network. So I wasn't introducing the GPU just to do the computational odometry. I already had a GPU, which was doing the pose regression in the first place. So all I'd done was added some layers onto an existing network. But I mean, it's a very valid question. I think it's horses for courses, isn't it? You probably wouldn't be interested in it if you've got a tiny little lightweight robot. But if you're an autonomous vehicle and you've already got, several discrete GPUs available to you, and there's some spare capacity, then why not use them?
Yeah, no, makes sense. I'm just quite, one of the typical problems we have now when we go on AgriFoRwArdS is battery lifetime. And you see all these robots, actually being able to cover quite huge distances now with good batteries. And the moment you put a GPU on it, it all falls down, right? It's interesting to see these days that actually the actual drive of robots doesn't take the most energy. It is all the computational performance we put onto it. So that was just a side note, whether that's always the it's so cool to see we can do all these different bits. And if you have already, as you said, if you basically use all the backends already to do all the clever bits, there's no additional costs really to also then basically see it through and do the localization with it as well. That makes sense.
I think at some point somebody's going to have to come up with a better architecture for GPUs. I mean, I think my brain's got quite a few processing units in it, but it doesn't draw anywhere near the power that the A100 or whatever in the my PhD student insists he must have access to. use it.
Yeah, because we are particularly good at, putting a lot of other parts of our brain into some energy saving mode when we don't use them, while GPUs probably are not very good at that yet. They usually doesn't scale, and people just kind of grab 100% if they can. Cool.
Why don't we just use?
That was my question.
Why don't we just use internal combustion engines? I mean, they generate a lot of power.
Well, we're gonna have
Never understood.
No.
But, I mean, anyway, whatever.
I think fossil fuels are going out of fashion a bit.
Yeah, it is. Yeah. But for agricultural vehicles, I guess we'll be stuck with them for some while, right? Because there's not many of them, and they don't really pollute very much. I have a question, but Shumin, did you have something that you wanted to ask?
Yes, I have a question. When you talk about the convolution odometry, this part, I say you use some computer vision technique, segmentation to help to the localization. I wondered, have you do any experiment which to compare with the localization from the LiDAR? I mean, for the localization error, how much the gap between the both of methods, or for the convolution odometry from the computer vision is better? Yeah, I wondered with this.
So I think, I mean, if you've got a decent map and decent depth measurements,
yeah,
then it's always going to do well. I mean, we compared CDAR with using a LiDAR, and we could get equivalent performance in the environment here using visual cues and triangulation compared to using a scanning LiDAR. For the computational odometry, I mean, as Mark sort of said, that's not really, I mean, you could do the same thing with MCL. That was just us being, I quite like just being a bit funky with the neural networks, and sort of like, because all of a sudden, all the stuff that we stopped doing because it didn't scale or was stupid, you can kind of becomes viable again because I've got all of this additional computational power. So that was just as being a little bit clever with a bit of spare GPU compute on the output of the network. And I quite like the idea that it's difficult to know when the classical neural network stops and a parallel implementation of some good old-fashioned algorithm starts. So, but yeah, the computational odometry thing really, I mean, it's just you could swap that. You could equally just use MCL. I don't think that would make a great deal of difference. The problem, I mean, it's the classic trade-off anyway, isn't it? It's only as good as the quantization levels. So we still, even though that GPU allows us to sort of like do things in parallel, you've still got a trade-off in that I've got a finite amount of space and I've got a minimum bin size. And if I get them wrong, it's going to suffer. I mean, fundamentally, it's only as good as the localization encoder, the thing that's trying to determine where it is. But I think what we did there it worked for that use case, because from Parkerpedia's point of view, it was about what assets could you capture that you could sell on, as an asset. So if you're going to map a car park, then and they don't want to do the localization. They want to sell an asset onto a car manufacturer that will allow their vehicle to localize in there. So it was really about asking the questions that if you're going to map an environment, what's the important things that you need to map, rather than what's the optimal algorithm, if that makes sense.
Okay. Sorry, I have another question. So also, I remember that when we did a project, I think many years ago, when we did a robot, indoor mobile robot, also use AMCL to localization. It's very when we use a LiDAR, it's just from the 2D LiDAR. It's very easily to lost the the initial location of robot when the robot reboot again. So I wonder this problem troubled us for several months, but we have not solved it very well. So I wondered if you use the image segmentation to assist you to assist the robot to localization. Could it solve this problem very good or not? Well, I mean, when the robot reboot shut down and you power it again, then it's very difficult to find the initial localization. So I think if we use the methods you represent from the image segmentation, could it better or not?
Okay, so I think, I mean, you're asking about relocalization. I think.
Yeah. When the robot, for example, when the robot reboot or robot, when the shut down the power and move the robot from one location to another location. I mean, moved by the human, not a robot. So it's very difficult to find the location again.
Well, but yeah, I mean, these are classic problems. I mean, the stuff I was talking about there, I mean, there were two things. So we were calculating visual odometry, and we were using the visual odometry as a differential to update the kernels.
Yeah.
But the localization is absolute, and that is absolute in a map. So in that case, what I was showing you there, it was always getting an absolute positional estimate on every single frame, but it was highly ambiguous, and it was using the kind of differential measurements to try and overcome the ambiguity in the natural ambiguity in the environment. But I mean, when you're out, I mean, isn't GPS the solution to everything? I mean, certainly when it comes to relocalization. I mean, if that robot gets lost,
yeah.
I mean, I'll be honest. So I don't know whether you use Colmap, but I mean, we constantly seem to be doing deadly battle with things like Colmap to try and get solid and uniform odometry, or just it's all very well. Somebody comes along and says, "Oh, just run bundle adjustment over it," but I mean, things are never that easy. And actually, for a lot of the car stuff, we do tend to use the LiDAR to get solid initial estimates and then fine tune localization with the vision, because otherwise the search problem just, I don't know. I mean, bundle adjustment seems to have been around for ages. Bundle adjustment was the solution to everything back when me and Richard were both lecturers, but have you ever tried to actually get it to work?
It's all right. Okay. Thank you very much for your representation. It's very wonderful.
Well, my
Yeah,
pleasure.
it was
Thank you very much.
wild ride, Richard. I mean, I think we've got time for this. Yeah. So I got a little bit confused in all of this, but right at the early part of your talk, you were talking about how people drive.
Yeah.
And that was the inspiration for some of this later talk, I think, where you do this semantic segmentation, and that allows you to work out where you are from the position of the segments or the items. Great idea. Now that's sort of tends to be a more sort of long baseline stereo, really, doesn't it? Because the vehicle moves from position to position, and that the movement might be quite long, and because the window is moved substantially from there to there, you can get quite accurate positioning. The thing I was pondering about as you were talking was that funny thing that people do, but owls do more. Were they sort of?
Oh yeah.
And I think what they're doing there is they're doing a semantic segmentation, and they're just watching the segments move. They're not doing short baseline optical stereo as we were taught it as kids. You know, they're doing this change in alignment between things. Do you see any of that in the work you're doing? It's a rather unusual way of doing range finding. It's popular with birds of prey. People do it when they're driving. I think they go.
Well, I'm not sure about that.
Okay,
I mean,
well, you tell me. That's what I think I do it a bit when I'm trying to. What is that?
I think I mean, going back to that really early work, I thought I got very excited. But eye gaze, oh, that's going to be brilliant. That's going to tell us loads of things.
Yeah.
And I think what I was trying to say in the slides was what I've discovered almost straight away was it was completely worthless until we dug down into the data. And once you've got the ability to find the fraction of a % of data that is good within the noise, then it's useful. But it's so dominated, you know, so that eye gaze data is just has got massive amounts of just random saccades that got nothing to do with attention.
That's just saccadic vision, man. That would be my argument. I mean, it's a bit like saying, looking at Constable's brushstrokes, can you work out he's painting the hay-wain? No, you got to see the whole thing build in front of you. Saccadic vision paints this scene, doesn't it? But did you measure head movement?
No. I mean, there was an awful lot of stuff recorded in that data, and I think we scratched the surface. I mean, we had things like, because I always wanted to look at like preparatory braking behavior.
Oh yeah.
Because one of the sensors we had, there was a proximity on all of the pedals.
Oh,
good. So we knew when somebody was putting their foot over the brake. Now, so I'm, you know, and I remember saying this a million times, but I'm sure that in that data, if we look at that preparatory braking behavior, there would be a correlation between somebody doing that and something happening. So if somebody puts the brakes on, maybe that's when you because it's all these things you subconsciously do.
Yeah.
But if that signal's in there, you know, it's such a weak correlation, and all the things you want to do at the beginning of a 3-year project when you've got the EU breathing down your neck about a deliverable that's due next week.
Yeah, I understand. Yeah. Right. Time really has pressed upon us, I think. Really
sorry, it's my fault.
I really enjoyed it. I saw some comments which implied the same, and that's great. I'm really grateful for taking the time out to do it for us. Lovely to see you.
You too. Look forward to seeing you without the box around you soon.
Yeah, it would be lovely to escape my little prison. But
and I hope you're feeling better soon.
I did so for an hour, so that was really nice. Thanks, and thanks everyone.
Thank you.
Cheers.
Bye.
Bye-bye.
Thank you.